we have Mr. Ruthvik Galem, a research assistant at the Bhaktivedanta Institute, Kolkata, and an alumnus of IIT Bhubaneswar. His topic is Bell's theorem, foundation, derivation, and implication for the quantum mechanism.
Let me begin with a short prayer. Om Jnanatimirandasya Jnananjanashalakaya Chakshurunmilitam Yena Tasmai Shri Gurave Namah Tasmai Shri Gurave Namah. Thank you so much for giving me this opportunity to present on Bell's theorem. So, if we see the history of quantum mechanics, one of the most important theorem is the Bell's theorem because it is one of the most mysterious thing. So let me just give you a short glimpse of what it is. So John Bell, he was actually working on CERN and he was actually working on the quantum foundations. So as he was already working on the quantum foundation, so many things inspired him. So one of such thing is like Einstein's philosophical concerns on quantum theory. Because when quantum theory first came, so it actually puzzled many people. So so Einstein philosophical concerns have like inspired John Bell to understand or to get his theorem. And this actually transformed the philosophical debate into testable scientific framework because at the end it became very influential. So to understand about Bell's theorem, first we need to understand about the EPR paradox, Einstein-Podolsky-Rosen paradox. So what happened is, so three scientists, Einstein, Podolsky, and Rosen, have attacked the quantum theory. It came in the news, but actually the paper name is "Can Quantum Mechanic Description of Physical Reality Be Considered Complete?" So this paper has come in 1935. So what it actually says is the EPR paradox. It has three assumptions. So first two assumptions are the predictions of quantum mechanics are correct, and and next one is about the criterion of reality. And the most important thing comes here is the physics is local. So this is important point to note. So in EPR paradox, the assumptions are like physics is local. So locality means, to simply understand, an object has effect only by its immediate surroundings, and that transmission or the communication can happen at the max the speed of light, not more than that. So this is what locality means. So these are the three assumptions made in the EPR paradox. And finally, the EPR conclusion, what it is the quantum mechanics is incomplete. So they claimed like this. So in the EPR paradox. But what happened is uh, John Bell. So he came up with an inequality, and then he questioned that EPR paradox. That was really interesting. So Bell formulated an inequality that all the local hidden variable theories must satisfy. So whatever this locality, what we are assuming, which is assumed in the EPR paradox, this locality, all the theories which satisfy that locality must satisfy one inequality. So he developed one inequality, and that will be satisfied by the all local theory, means whichever accept the locality. And surprisingly, what happened is these quantum mechanic predictions violates this inequality. Since this inequality is violated, locality is not possible in the quantum mechanics. So that is what is the conclusion is it is non-local, right? So we were trying to understand about this assumption, non-locality or the entanglement, what we are studying about. An effect here has an immediate effect at the very longer distance, right? And this effect can be faster than the speed of light. So this is what something tricky or something new. So because of this inequality, one thing is it we came to understand that the signal or the communication can happen faster than the speed of light. Because the effect has another effect on the other part of the place which can be faster than the speed of light. So to simply understand, because Bell's inequality is very complicated, but mathematically to simply understand, let me show you here. So by the simple sets, we know that a you can see there are a, b, and w. Okay, so here probability of a intersection b. You can see this area, right? A intersection b. So this should be less than or equal to probability of A intersection W plus probability of which is not W and intersection of B. So this part. So all the local variables or the locality should satisfy this inequality. But in the quantum mechanics, this inequality is violated. So that is really surprising. So he came up with an inequality, and this inequality is violated by the quantum mechanics things. So this has a lot of good implications in the quantum mechanics. The theory or the derivation is very big to understand, but I just gave a short glimpse what it is actually, so that you can go back to your home and explore. So if you see the implications for the quantum technology, uh, it confirms the entanglement as real usable phenomenon. So it clearly tells that entanglement can happen, because what happens in the locality, only local things affects the particle, and that cannot happen more than the speed of light. But entanglement is very special, so it can affect at a very longer distances. So it has a very important application in the quantum computing, cryptography, and even in the teleportation. So these are the very much important implications of the quantum technology. And the quantum system defy the classical expectations. So quantum systems, we already know that, right? So since 3 days we are understanding there are many different things which are going beyond the laws of what we understand and what we assume. So, and because of this Bell's theorem, three scientists who recently got Nobel Prize in Physics in 2022, who is Mr. Alan Aspect and Mr. Cluster and Zeilinger. So these three scientists got the Nobel Prize for actually for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So this Bell inequality is very profound, and recently they got the Nobel Prize for working on the Bell's theorem. So to conclude and for the discussion, so Bell's theorem bridges philosophy and physics, because if you see, signal can pass beyond the speed of light, or it can be more profound, because in some of our lectures in the previous days, Shri Varun Agarwalji was discussing about these things. Someone was discussing with him, can this message or can this information pass from the very longer spiritual dimension to the our world, or can there be any other medium, or what transmission can happen? So they are questioning, or they're asking like how this can happen. And experimental revolutionize our view of reality. Yes, that's true, because this one important Bell's inequality has really made us, because we want some solid theory or the proof. So this inequality which is violated is actually showing that yes, this entanglement can really occur. And ongoing research continues to probe the quantum world. So of course we are further progressing. And quantum, thank you.
Bell's theorem says that a local realistic hidden variable theory cannot reproduce quantum mechanics.
Okay.
So Bell's theorem doesn't say anything about quantum mechanics. It says something about hidden variable theories. That's all. So if it's like if somebody comes and tells me I'm not like Shah Rukh Khan, it doesn't say anything about Shah Rukh Khan. It tells something about me. So all the successes of quantum technologies are quantum mechanics. It has nothing to do with Bell's theorem.
Okay. So, but the entanglement, which is
It is quantum mechanics.
okay.
Even if Bell hadn't written the paper in Bell's theorem, there is still entanglement in the quantum world,
Okay. Okay.
right?
Yeah. Yeah. That's.
So I think this has been said over and over again. Even Nobel Committee said this, that they said it's all about quantum mechanics. And my reaction to that is the prize is for something that is not about quantum mechanics at all. It's about hidden variable theories.
Okay. Okay. So thank you. Fine.
Just to add a line or two to what Professor Haridas said,
Yes.
I think we will agree that an implication of Bell's theorem is that nature is non-local, one possible implication. And if it is non-local, we have to ask, does it violate special relativity? And if we agree, yes. So then we are asking this question, does that mean this is in contradiction with special relativity or not? If we agree that it is in contradiction with special relativity, then we need to do something more. Either modify quantum mechanics to make it consistent with relativity, or modify relativity to make it consistent with quantum mechanics, or modify both. So I think I agree with you that it's not a statement about quantum mechanics, but it as a subset is that it says that a theory like quantum mechanics, if it has to describe nature, has to be non-local. And then I think we have a problem, in my opinion, a problem about which we need to do something.
You can go along with that.
Thank you.